So now we have a different subject, Schnyder orientations for d-irreducible maps by Eric FUSY. Thank you.
Okay, thank you very much. So it's a great pleasure for me to talk for Emmanuel's birthday conference. So let me, go to when I started really working with Emmanuel. So it was actually a journée carte 12 years ago. It was here. It was over 2 days, and there was a very beautiful bijection by Timothy. So there are common points with this conference. And this one was the ambient bud bijection, and it was very simple. We knew very well the Corey-Vauquelin-Schaeffer bijection, where you start from quadrangulation with distance labeling, and in each phase you connect the two corners that are at the end of label ascent in clockwise order. And here, what you do is you connect the two corners that are at the end of a label descent when you do a clockwise contour. And amazingly, it gives a bijection between quadrangulations and maps. So there was already a well-known bijection due to Tutt, but this one preserves the distance to the wood vertex. So it was very amazing, and we got very excited, and we started to discuss with Emmanuel and Jeremy and play with this bijection, and we came up with extension to hypermaps and constellations. So there are different families, and we have I think Jeremy did this very nice diagram with all the families we had in bijection. So it was really really thorough investigation of all these links. And then I decided to continue to work with Emmanuel on related topics coming from this ambient bud bijection. And we looked at bivariate extensions of the two-point function. So the bijection essentially gives that the two-point function of quadrangulation is the same as the one of maps. And then in the ambient bud paper, there was a nice bivariate extension of the two-point function where you have a parameter which are, the second parameter is the number of local max, which is the number of faces of the maps. And with Emmanuel, we also look at another bivariate extension where we look at the number of odd label vertices. So this gives the number of faces of the map, but via Tutt's bijections. And it turns out that two-point functions has nice expressions in both cases, and we tried to do, we looked at the derivation with continued fractions. And it worked very well for the first extension, and we could even do the extension to the BDG setting of bipartite maps instead of quadrangulation. So the second one with continued fractions was with more struggle. We still have the nice derivation, and there was connection with work of Philippe on finite continued fractions, and some connections with heaps. And so I introduced HYPE to Emmanuel, and he learned very quickly, and he made this beautiful drawing of heaps for the second work. And so today I'm talking about a topic where I didn't work directly with Emmanuel, but we have, I think there is some connections between our methods, and I want to show also some recent work I did with Olivier Bernardi and his students on this topic. So it's about counting about the girth parameter on maps and counting maps with girth constraints. So the girth is just the length of a shortest cycle. So it can be defined on a graph. And so a simple remark is that if the girth is d, then all faces have length at least d. And there is a second parameter, girth parameter, where you need a planar embedding really to define. It's a non-facial girth it's the length of a shortest cycle that is not the boundary of a face. Okay, so for the first map, the two are the same, but for the second one, the non-facial girth is 5. It's 5, I think. But you have face contours of degree 3, so here it's a different value. And then there is this notion of d-irreducible maps. Oops. I don't know. It's stuck. There is a kind of. Okay. So d-irreducible maps are maps where the bound on the girth is a d, but you want that non-facial girths are strictly larger than d. And it's a natural notion also. For instance, irreducible quadrangulations were known to be in bijection to 3 connected maps. So irreducible maps have been, it's a constraint that has been considered for a long time in the enumeration of maps. And also, it's also very useful as an intermediate family, the irreducible maps between maps of girth at least d and at least d plus 1. So, of course, it's a stronger condition than being of girth at least d because you add something to the non-facial girth. And it's also clearly included in maps of girth at least d plus 1 because if you don't have faces of degree d, then these ones are exactly these ones. Okay, so it's kind of a convenient intermediate family. And actually, it's very useful. And this is a nice work by Emmanuel and Jérémy. If you want to do counting of maps by girth and face degree with a substitution approach, and irreducible maps allows to jump from girth d to girth d plus 1. And so the idea is to have this notion of d-irreducible core, where you start from maps of girth at least d. So here it's a simple map, for instance. And what you do is you empty what is inside all the maximal 3 cycles. Okay, like here. Turns out that there are interior disjoints, and what you get is a 3 irreducible core of the map. And it gives a nice equation system relating maps of girth at least d with the d-irreducible maps. So you see that faces of degree d are replaced by maps of girth at least d and outer contour d. And then to jump to girth d plus 1, you just say that there are d-irreducible maps with no face of degree d. Okay? And using this equation system, you can carry algebraic expression for maps with a certain boundary length, outer contour length. And actually, for the first value, you can use the bijective approach, so with slices or with mobiles, and also with functional equations, as shown by Gilles yesterday. But it seems it's not obvious. It's probably not very convenient to get functional equations to maps of girth at least d, for instance. So really, it's convenient to do this substitution approach. And so about the method, so there's this substitution method, and it was also applied by Timothy and with Alicia to the context of metric irreducible maps with possibly higher genus. And about bijective methods, there are essentially two main methods. There is a slice decomposition by Emmanuel and Jérémy, which was also recently also used and developed further in a paper with Hugo Manet, and also used in related problems where you have cycle constraints. So there is also this nice paper with for counting maps with tight boundaries with Gregory. And in this talk, I will review an approach I developed with Olivier Bernardi, so a long time ago, which for doing bijective enumeration via orientations. And we obtain bijection with certain families of trees. And we have come back to this more recently with Olivier's PhD student. So I will show in the second part. And yes, I had a discussion with Emmanuel and Jeremy about also, so there are some connections between the method and that the recent work with Hugo can make also give a way to obtain the orientations for these maps with girth constraints. I will also mention some kind of links between our approach and the substitution method. So there are some links between the three approaches. Okay, so let me show how it works, this approach with orientation. And so the starting point is, of course, a BDG bijection. So it's, it was already described yesterday, but let me recall. So you start with a bipartite map, and where with the distance labeling, and around each face, you put a black vertex in each face, and you connect it to all corners that are at the end of a label ascent. So it's an extension of the Corey-Vauquelin-Schaeffer bijection. And the local rule for each edge is shown here. And what you obtain is a tree with labeled two types of vertices and labeled white vertices. And so you have the constraint that the labels are positives and there is a one somewhere. And also that around black vertices, you have this constraint that the jumps are at least -1 for consecutive values. And so actually this bijection can be reformulated in a context of geodesic orientation, where you just forget the labels and encode the labeling by the orientation towards the wood vertex. Okay? So you go from I to I-1. And for the mobile, you can encode the label jumps by some buds, which you put in corners. So if you have a label jump delta, you put delta plus 1 bud in the corner. And the mobiles you obtain here, they are unlabeled at white vertices, but it's encoded by these buds, and you want black vertices. They have even degree, and they have as many buds as edges. Okay, so that's the only condition. So it's quite a simple rule for the trees. And also you can see that you can obtain this blossoming mobile directly from the oriented map by applying this local rule at each edge. So for each oriented edge, you put a red edge from the origin to the black vertex in the face on the left, and on the other side you just put a bud pointing to the extremity of the edge. Okay, so and this local rule will be the one we will have in our general bijection. Okay, so actually this now we can try to apply it to other orientation than geodesic orientation. Okay, and turns out that what is important is that the orientation we have are accessible, so meaning that from each vertex you can reach the sink. So here actually we can also take a sink that is not necessarily a single vertex but can be a digone. It will be convenient for the families we consider. And we don't really need the orientation to be acyclic, but just to have no clockwise cycle. And with this condition, it's if we apply the same local rules at each edge, and also this rule for the outer edges, then we obtain a tree and a blossoming mobile. Okay. Okay. So now we don't necessarily have as many buds as edges around black vertices, but we always get a tree. We call this blossoming mobiles. And actually, it's a bijection. Okay. And we have some correspondence which we can use to specialize the bijection. So the D is the length of the sink, so the digone corresponds to an excess parameter, which is a number of buds minus number of edges. The degrees of the interfaces translates to degrees of black nodes in the mobile, and the degrees of interfaces translates to degrees of white nodes here. Okay, so it's quite a simple correspondence. And actually, yeah, in the specialization, this will be no problem. So this will be redundant with the other conditions. So I will not go back to this. Okay, and the inverse bijection, I will not show in general. I will just show the directions from maps to trees, but it relies on some closure operations, as in Gilles' construction in his thesis, which can be formulated by growing a cactus from the tree and like matching some edges of the boundary of the cactus by a sort of parenthesis matching. Okay, so you obtain your oriented map back. Okay, and so there is also this condition of having a minimal orientation, and it turns out actually it's convenient to apply to maps because this minimal orientation, they will play the role of sort of canonical orientation. And the key result is that if you have an orientation with prescribed outdegrees, then you have a unique minimal orientation. So we call minimal is that you have no clockwise cycle. You have a unique one with same outdegrees and no clockwise cycle. And actually, to obtain it, you can just greedily return clockwise cycles until you have no clockwise cycle. And the one you obtain is always doesn't depend on the order in which you do the operation. Actually, if you want to do the computation, an algorithm to do it, there is a simple way. It involves a kind of distance function in the dual, but where you travel cost is 1 to go from left to right, but 0 to go from right to left. So it's a very economic distance. And if you compute the distance with this, you will have the property that for each edge, the label on the right side is either equal to the label of on the left side or 1 plus. And if it's 1 plus, you return the edge. And what you obtain is the minimal orientation. Okay, so it's really a simple algorithm to go to the minimal orientation, and we will use it as a canonical orientation to apply the bijection. Okay, so let me illustrate it on the simple triangulations. So what the orientations that characterize the family are the 3 orientations in that case. That for triangulation, the number of internal edges is 3 times the number of internal vertices. So it suggests that we could hope for an orientation without degree 3 at each internal vertex. And it turns out that such an orientation exists when the triangulation is simple, and if and only if it is simple. Okay. So if it's not simple, then you can see that you have not enough edges inside the bigone to accommodate for having out degree 3. Okay, for instance, here we have only 2 incident edges. And if it's simple, actually there is an algorithm to compute a 3 orientation. So I don't show it, but it's a vertex shelling procedure which goes from top to bottom, and where you propagate the orientation to obtain a 3 orientation. So originally it was applied, these structures, to have a beautiful straight line drawing algorithm by Schnyder based on a phase counting operation. So it's also a motivation to use this orientation. But here I will not use this colored incarnation, just the orientation. Okay, so now we can apply our general bijection, which we specialize to simple triangulations. So we start from a simple triangulation. We ender it with the canonical, the minimal 3 orientation. We apply the bijection. And what we obtain is a blossoming mobile, and the constraint that phase degree having degree 3 means that black vertices have degree 3 here, and here vertices have out degree 3 is white vertices have out degree 3. Okay, so now these trees can be counted easily. So we have to deal with the root. So here we don't have a root. We have only unrooted tree, but it's quite easy to deal with the root, having a root in the outer face. And it's a way to recover in a bijective way the formula obtained by Tutt in his census paper on triangulations. So it was a special part of a bijection we had with Dominique Poulalon and Gilles Schaeffer. And there is a different bijection by Poulalon and Schaeffer, which relies on now the tree associated to the orientation is a spanning tree, which you derive from the orientation. And so now we wanted to push further this approach to d-angulations of girth D, for instance. And we have this observation. It's an extension of what happens in the triangular case, that the number of inner edges over the number of inner vertices is d over d minus 2. Okay? So this suggests we could hope for having an orientation where each internal vertex has out degree d over d minus 2. Okay? So it has not much sense for d larger than 3. But we can make sense of it by duplicating every edge into d minus 2 copies. So here for d equal 5, you make 3 copies of each edge. And now we can hope for having an orientation where so each vertex has out degree 5. Okay? And actually, we prove that this happens if and only if the d-angulation has girth d. Okay? So it's a similar, for necessity, it's similar that what you had in the triangular case, that if you have a short cycle, you don't have enough edges inside to accommodate for the out degrees. And for the existence part, we didn't manage to find the vertex shading procedure, but we can rely on some general criteria which are similar to Hall's marriage theorem. Okay? So kind of having inequality satisfied everywhere ensures existence. Okay? Well, in terms of algorithm, it's not very efficient, and we wanted to have a sort of more direct computation method, and actually we managed to find one recently using these irreducible maps. So, okay, but let me, sorry, it was not maybe the good point, the good time, but let me also, yeah, I was at this part on the orientation, yeah, and so we can now apply the general construction, which we can extend to this orientation with duplicated edges. So actually, I forgot to say that this can be formulated with flows, okay, which, as you can see here. We can generalize this general bijection to this setting of biorientation with flows. So you can see that for the edges that have positive flows in both directions, we have a new local rules here. Actually, we just keep these edges in the tree. They are the black edges with one bud for each corner. And actually, just that this mimics the fact that these edges can be seen considered as counterclockwise bigons. So if it were counterclockwise bigons, it would give 2 edges traversing the bigon. Okay, so in any case, we have some simple local rules in these extended settings, and which also preserve the degrees of inner faces and the total outgoing flows of vertices. And we can apply it to the d-angulation of girth D and obtain some models of trees with kind of flows on the edges and some simple flow conditions at edges and at wide vertices. So which gives an algebraic expression for the generating function. So, and Marie Alban and Dominique Poulalon, they have another bijection with weighting blossoming tree, which is the extension of the Poulalon-Schaeffer bijection. Okay. So as in the BDG bijection, the trees are simpler in the bipartite case. So there is a simplification at the level of orientations that actually yeah, if the girth is 2b, then the d over d minus 2 of the outdegrees becomes b over b minus 1. And actually, for instance, this occurs for simple coangulations. We really have just orientation of outdegree 2. And when we apply our general bijection, we recover a bijection of Gilles with trees that are essentially unrooted ternary trees. Okay, so now, yeah, as I said, we were not completely satisfied with the way we compute this d over d minus 2 orientations with this just general existence criteria. And we wanted to have an approach also for the irreducible case. So let me show the example on irreducible triangulations. So here, I don't want the outer face to have degree 3, so there are some pathologies. Particularly, the irreducible core would be empty. So I take it a little larger, so 4. And I consider irreducible triangulation. And there are some also some outdegree constrained orientations, but in the angular map, so the quadrangulation associated to the triangulation. So the black vertices have degree 3, corresponding to the triangle. And actually, the orientations, they have outdegree 4 at white vertices and outdegree 1 at black vertices. So they are a little more complicated, but they are very natural if you think that these triangulations, they are the ones that can be the dual of rectangulations, okay? And now this orientation, it just corresponds the 4 outgoing edges at white vertices that correspond to the ones going to the 4 corners of the corresponding rectangle here, okay? So this orientation can also be computed by some vertex some shelling procedure, and they give rise also to a bijection. So here the little difficulty is that we have no control really on the vertex degrees. We have control on the vertex out degrees. So here we ask the black vertices to have degree 3, so it's not very convenient to apply the bijection on this. So we do something we use frequently is to do a transfer of orientation. So we transfer the orientation to the half edges of the triangulation using these rules, and it turns out that the orientation of the half edges and the bi-oriented edges they form a tree, okay? And you have out degree 4 at each vertex, each internal vertex. And when you erase the ingoing half edges, you obtain an unrooted ternary tree. Okay. So it's actually, yeah, it's an example where we really, it's more convenient to transfer first before applying a bijection. And there is a similar bijection for irreducible quadrangulations, which I obtained with Dominique and Gilles. And yeah, it can also be obtained from our general construction, even if it's not really necessary here, but yeah, it works also. Yeah, I'm not very much time, probably. Oh, yeah? Two, okay. Okay, so I will briefly show that actually there is now just on the computation part of the orientation, we can compute this orientation starting from the 3 orientations and start to kind of build an induction. So we we start from a 3 orientation, which we obtain from augmenting into a triangulation and computing a 3 orientation. So, and we look at what we obtain. And so what you can see is that internal vertices have out degree 3, but there is also one edge coming out of the outer gone, outer quadrangle. So now we can look at what vertices are reachable from the outer contour, and it turns out that they are exactly the irreducible core, which I showed for the substitution method. Okay, so what is inside a triangle cannot be reached because everything is going towards the vertices of the triangle.
Oh, there is something else. Why there is this arrow from the... There is a single arrow from the...
Yeah, that's a general property that if you have a cycle, you have of length d, you have d minus 3 edges going inside. So and in part, yeah. So that's why it's 1, and for the ones of 3 there is 0, and that's why they are not accessible from the outer contour. So the vertices that are accessible from the outer contour are from the irreducible core, and in particular, the triangulation is irreducible if and only if the orientation is said co-accessible, meaning that all vertices can be reached from the outer foreground.
Sorry, again, what is on the previous picture?
Ouais.
I see that the top right corner, the top yellow, what does the yellow regions mean on the top right? Is because of the...
These are what is emptied to obtain the irreducible core. What is taken out when you compute the core. So you empty the maximal triangles, so the non-empty triangles.
But what is the connection with the red arrow from inside?
Nothing. I think. Yeah, it's outside yellow arrow, but it could be. I guess it could not be on the boundary of a yellow region. Okay, so now we have a characterization of irreducibility. It's that the orientation is co-accessible, and so we can use a co-accessibility spanning tree. We fix any co-accessibility spanning tree. So they are the ones that go away from the outer contour. And now we have a simple way to compute an orientation, angular orientation, as I showed, that for each external edge, you mark a corner which is in the face just inside and at the extremity of the edge, like this, okay? So what is very easy to see is that each internal face has a unique marked corner, and also quite easy is that each internal vertex has 4 unmarked corners, okay? So this is just what we need, and if we apply this simple rule, we obtain the angular orientation. So it's a very simple way to compute it from building from what we had for simple triangulation, the orientation. And so what we had at this step is we start to build the induction. So what we have is that if we have orientations for, more generally for d-angulations of girth d, we can obtain orientations for irreducible d-angulations of the d+1 gone. And we have something similar for the bipartite case. Okay, using this co-accessibility property. And the question is now, can we go to girth d+1 a bit similarly to the substitution approach? And actually, it's also quite simple. So for this, also very simple here, from 3 irreducible to girth 4, the idea is to just put a vertex inside each face connected to the 4 corners. So you get an irreducible triangulation. You compute angular orientation. Then you just delete the added vertices, and you can see that for each, essentially, you get a 4/2 orientation. So here the 2 edges has to agree, so you just smooth out the black vertices. And here you have outdegree 4, and here also. Okay. So you directly obtain the d over d minus 2 orientation for d+1. Okay. And similarly for the bipartite case. So we have now we have induction working, and there is so I discussed with Jeremy and Emmanuel last year, and it's also possible to arrive to this orientation using the slice decomposition, okay, and without induction, I think. So here we were still a little bothered about one point, is that if to go from d to d+1, we need d to be odd, okay? Because here you triangulate the 4 cycles. So if you want to go from 4 to 5, you need to quadrangulate the 5 cycles, and it's not possible. And so it was a little annoying. So we came up with an extended notion of irreducibility, which are called d-maps. Now it's just that the phase degree can be arbitrarily lower compared to the band, the lower bound on the non-facial girth. Okay, so here you say the non-facial girth is at least 5, but you can have faces of degree arbitrarily lower. And with this approach, we have more flexibility with the face degrees, and we can carry the induction from D to D+1, whatever the parity of D. And we can also have some wood, some labelings, and so on. And let me finish with the examples. With a strong irreducibility, there are the d-angulation of a 2t minus 2 gone, where the non-facial girth is 2d minus 2. So for d equals 3, d equals 4, it's irreducible. For d at least 6, it's empty. But for d equals 5, it's something new. So it's some new family with where it's a kind of strong irreducibility because the face degrees are 5, but not facial girth has to be 8. Okay, and so it's a bit mysterious how to count this bijectively. So I will stop. Okay. Thank you.
Is there an urgent question? Yes.
Sorry for.
So if I understand on the previous slide, so you have some, you talk about this scheme of going from irreducible, girth D+1, d-irreducible, and girth D. So this is a generalization of this, if I understand correctly, the same scheme for your
exactly.
approach with orientation.
Yeah.
And for this, would there be also a substitution approach?
I think, I'm not sure. So I think there could be a problem that, but maybe it works. But if you patch into D-gones, into D faces, you may have, I think, well, you may have maybe some situation where, so you are allowed to have very small faces. So it maybe could happen that by patching into adjacent faces, you could create a small cycle with vertices inside. So this kind of thing at the boundaries of the D-gones where you patch the maps. So this is, maybe I'm wrong about that, but I thought there might be an kind of problem here, the substitution.